Okay, today we are going to talk about the inner product, length, and orthogonality. So this is start of the section 6 in our textbook. Until last week, we've talked about the determinant, right? So okay, so by the way, there's homework number 2. So due date of this homework is May 21, maybe Thursday, right? So Thursday until midnight. So please submit your homework in Blackboard as usual. Then the problem is to solve the following problem set in our textbook from section 2.1 to the section 3.2. So it means there is the solution set, the problem set from the section 2.1, 2.2, 2.3, 2.4, 2.8, 2.9, and 3.1 and 3.2. Okay, so this is the homework 2. So you must submit photograph or the scanned file electrically in Blackboard. So as usual, we have a late policy as a 25% off per day late. So by the way, in homework number 1, there was some student who submitted lately in about 10 minutes, something like that. But in from this homework, we cannot receive the something like the late. So please try to submit your homework as soon as possible. Okay. So and then what else? Yeah, homework should be written in English, right? Then please do not copy your friend's one and please start your homework early. Okay. So this is the notification of the homework number 2. Homework number 2. Okay, let's start today's lecture. Before starting, there was a question about related to our lecture 5.1, right? In our lecture 5.1, there was a property of the matrix multiplication, but when I explained this property, I made some mistake. For example, if in this property matrix A has the m rows and n columns, right? So it means that the size of the matrix A is the m by n. Then the matrix B and matrix C have size for which the indicated sums and products are defined. It means that the size of matrix B and C might not same as the size of matrix A. For example, in here, the size of the matrix B, because the size of matrix A is n by n, so size of matrix B should be n by arbitrary number, let's say k1, right? And in this case, the size of the matrix C should be k1 times k2, right? So in this case, the output of this computation would be m times k2. Okay. So please keep in mind to compute the matrix multiplication. The number of columns and number of rows should be same between A and B. Okay. So please check this property again. Okay. Let's go back to our today's lecture. Okay, today we will talk about the inner product. Actually, this is the geometric concept of the vectors or matrices. So we will define how can we measure the similarity or the relationship between the arbitrary 2 or 3 vectors in the vector space. So okay, let's start. So if the vector u and v are in Rn space, right? For example, vector u is something like u1, u2, un, right? And matrix vector v is v1, v2 through the vn. We can say that these two vectors are n by 1 matrices, right? So it means that we can compute the transpose of the vector u, right? Then what is that? u1, u2 through the un, right? So comparing to this one, it transpose u only have the one row, right? Then this is the 1 by n matrix, right? Then the matrix product u transpose times v in here u transpose times v is equal to u1, u2 through un times v1, v2, vn, right? This is n, right? So because the size of this matrix is 1 by n, and size of this one is the n by 1, right? So what is the size of this matrix computation or matrix product? Just 1 by 1 scalar value, right? Because when we compute the matrix multiplication, we just compute this compute the product between this vector and this vector, right? So if you remember this one, we just compute this row times this column in matrix product, right? So output was some kind of the scalar, right? So in this case, this scalar value is called the inner product. Inner product or top product. Okay, so in other words, we can represent the inner product between matrix U and matrix V as a U transpose times V or U dot V. So this is the definition of the inner product or dot product. Okay, we already used this concept when computing the matrix product in our lecture, also matrix multiplication chapter. So we already know this, but this is just the systemical definition of the inner product. Okay, so concretely, if the vector u is something like this, right? So vector v is something like this, then inner product between u and v is u dot v or u transpose times v, or we can call the inner product of u and v is going to be u transpose. So this is the one row, right? And v vector v, right? Then how can I compute this matrix multiplication? How can I compute? This one times this one, right? So u1 times v1 plus this one times this one. So u2 times v2, then finally u1 times v1. Okay, so the inner product of the u and v is defined something like this. So the summation of the multiplication of each element in the vectors. Okay, so this is the definition of the inner product. Okay, let's see one. Where yeah, let's see the one example. Yeah, here. Okay, so for example, let's say vector u is something like 2 minus 5 negative 1, and vector v is something like 3 2 negative 3, right? Then compute top product a u v. So how can you do that? Just the element-wise multiplication. So 2 times 3 plus here, and here. So negative 5 times 2, right? Then and then negative 1 times negative 3, right? So negative 1 times negative 3, right? So it will be 6, negative 10, and 3. So it will be negative 1. Okay. So this is very intuitive, right? So this is the definition of the inner product. Because the inner product is defined with the transpose, matrix transpose, so it has a similar property of the matrix transpose. For example, if we go back to our lecture 5.1 here, we've discussed matrix multiplication property, right? And matrix transpose of the matrix property, something like this, right? Here, this inner product was the U transpose of V and V transpose U. Then it means that we can use this property of the matrix transpose of the matrix and matrix multiplication. Okay, so let's see. So let's say there is a matrix is U V W. Because the matrix U V W defined in the Rn space, so let's say this is just a vector, right? So because the shape of this matrix something like this, right? N by 1, something like that. So, and then let's say the C is the scalar value, right? Then there are 4 following inner product property. So first one is inner product of the U and V is equal to inner product of V and U. So you can easily prove this concept by using where is that? Matrix times U, where is it? Or we can easily verify this one. For example, U transpose times V was the U 1, U2, UN, right? And V1, V2, Vn, right? So U1, V1, U2, V2, Un, Vn. This is the left hand side, and right hand side means V1, Vn, and U1, Un. So U1, V1, Un, Vn. Okay, so because these two equations are same, so we can prove this one, right? So This is very intuitive property. What else? U plus V times U plus V a dot product of the U plus V and W is equal to dot product of U and W plus V and W. Okay, so this is the inner product. This is just the commutative rule. Okay, let's see the lecture 5.1. There was the theorem, something like this, right? So as you can see here, the A times B plus C was equal to A times B plus A times C, right? So in our case, here, right? So in our case, A is this one, right? So W, it means that this is the U plus V transpose W, something like that, right? And U transpose W, V transpose W, right? So as you can see here, here's that W, yeah, here. So from this one, P plus C times matrix A equal to P times A plus C times A, right? So in our case, U plus V transpose times W is equal to U transpose times W and V transpose times W. Okay, so this is another property of the inner product. And what else? C times vector U and dot V is equal to C times U dot V and U dot CV. Okay, so this is also very intuitive. Why? Because the C is, this one is equal to C transpose U V is equal to C U transpose V, right? U transpose of CV, right? So because the C is the scalar value in here, right? And matrix transpose is also just a matrix, right? So it just follow this property, right? So we can prove this one. And inner product of the U and U, if is larger than 0 or equal to 0, then inner product U and U is equal to 0 if and only if U is equal to 0. So it means that if some arbitrary vector satisfy this statement, then it inherently inherently means that U is equal to 0. Okay, then in other words, if U is equal to 0, then dot product U is equal to 0. Okay, so this is the full property of the inner product. Okay, so we can easily use this property to prove the following theorem. Okay, so and then by the way, this property B and C can be combined several times to produce the following useful rule. So what does it mean? If the if there is some column vector u1, u2 through the up, and their linear combination with some scalar value c1, cp, right? So what was that? Actually, this is the kind of the span, right? u1 through the up, right? Or linear combination of the u1 through the up, right? Then this one, the transpose inner product of this vector and vector w is equal to c1 times vector u1 w, inner product of the u1 and w, okay, and cp up and w. So what does it mean? This is actually, this is just a scalar value, right? Scalar value, right? So it means that this is the linear combination of the output u1 dot w and up dot w. Okay, so this is the useful property that we can use in the following, which was derived by property B and C. Okay, so you can derive from left hand side to the right hand side by yourself using the property B and 3. Okay, so this is the definition of the inner product. Let's move on to the length of the vector or the distance concept. Here's the definition. The length of the vector v is the non-negative scalar. This one. This is the definition. This is a notion of the length, which is defined by here. The length of the v is equal to square root of the inner product v and v, or the v dot v, and this one is equal to square root v1 square plus v2 square plus blah 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 and vn square, right? So for example, let's say we have a matrix something like 1 2 3 1 2 0, then the length of this v is equal to v transpose v v dot v, then this is actually the v transpose times v transpose times v, right? Then what was the v transpose? In this case 1 2 0, and original v was 1 2 0, right? So which means this is the 1 times 1 plus 2 times 2 plus 0, right? So finally 1 2 by 2 is equal to 4, so this is equal to 5, right? So this is the length of the vector v. So length of the vector v is the square root of 5. Okay, so this is definition. And the square of the length of the vector v is equal to v transpose v, right? Why? From here, right? So this is just definition. Okay, so okay, let's think about this meaning. Okay, let's suppose matrix vector v is in the R2 space, right? So and the vector v is something like A and B, then we can represent this vector v in the 2D space, right? Or the R2 space. X consists of the x1 and x2, right? we can represent this vector v in here, right? So this is just vector v. Then we want to know the length of this vector. We want to know the length of this vector, right? Then how can we compute this one? How can we compute the length of this vector? If you remember the Pythagorean theorem, which was a very popular theorem in our middle school life, right? So there was a Pythagorean theorem. How can you do that? Okay, if we know the length of this one and this one, then we can compute this one, right? In this case, the length of this one is just a, right? Because this is a comma b, and length of this one is the b, right? So this length is compute square root a square plus the b square, right? So this is a similar meaning in the length of the v, right? So as you can see here, if we define the v with the geometric point in the plane here, in here, then the length of v coincide with the standard notion of the length of the line from the origin to v, right? So which follows from the Pythagorean theorem applied to the triangle, right? Because these two lines are perpendicular, right? So this is the intuition of the length of the vector. Okay, so and then for any scalar c, the length c times vector v is equal to absolute c times length of the v. So let's say we have the arbitrary matrix v in 2D space or the R2 space. The one vector v is in here, right? Then okay, let's represent something like that. And if you multiply the scalar with c, the shape of the CV looks like this one, or this one. If the sign of the scalar value c is negative, then the shape of new c times v when c is negative and c is positive, right? Then length of this new CV here or here is equal to length of this one times just c. Okay, so in other words, the length of the v here and absolute value of c, so this one times c is equal to this one. Okay, so it will be equal to this length. Okay, so this is the first line, and there's one more definition. A vector whose length is 1 is called the unit vector. Okay, so let's think about the two-dimensional case also. If we have the main vector v here, then and if the length of this v is 1, then this vector is called the unit vector, right? Is there any other vector that satisfy this one? Yes. Where? Here, right? Or here. Or here, right? If they have the same length here, these three point also called the unit vector, right? So if we find out the every point that satisfy this one, they will make some kind of the circle has the whose length is 1. Okay, so this is called the unit vector. Then if we divide the non-zero vector v, by its length, that is multiply 1 over length of v, we can obtain the unit vector u, because the length of u is the here. So let's redraw. So let's say we have a matrix U whose length is larger than 1. Then, and if we multiply 1 over v, then we can make a vector this one just v, and this one is v. So in here u is equal to v times v over length of v, right? So in this case, the length of the u is equal to v, so it should be 1, right? So it means that this vector u is the unit vector, right? It means that, okay, so any vector in this line, can be normalized as a unit vector. This one, okay? So this process of creating u from v is sometimes called the normalizing v, and we say that u is in the same direction as v. So as you can see here, u is the same direction as v. Okay, why we need this? Why do we need a unit vector? Because actually sometimes the length of the vector is not important. Actually sometimes, okay, let's think about some intuition. Let's say there is a two vector v1, v2, v3. Then we want to know these 3 points, the relationship of these 3 points. We want to know v1 and v2 are similar, more similar than the v1 and v3, or we want to know the v2 similarity between v2 and v3 larger than v1 and v2, something like that. Because okay, if you think about just the scalar value, we easily know that if we have the 2, 3, let's say 7, this relationship is the smaller, is larger than this one, right? So, but in vector space, we need some kind of the distance term, right? So it means that, okay, how can we know this one is much the similarity between 2 and 3 is larger than 3 and 2, we just measure the distance, right? Something like 2, 3, and 3 negative 7 this. So we know this one is larger than this one. So we can easily do that. So, but in the vector space, we need tools to measure the similarity between arbitrary vectors. So that's why we introduced the inner product and the length of the vector. So it means that if we can normalize this vector v1 to the unit vector, let's say u1, v2 to the u2, v3, and u3. Then by comparing to the u1, u2, u3, rather than comparing the v1 and v2 and v3, we can easily find out the relationship between unit vector u1, u2, and u3. Okay, so from now on, let's find out how can we measure the similarity between the vector u1, u2, u3. Okay. So before that, okay, let's see the one more example. Let's say we have a vector v is equal to b 1, negative 2, 2, 0, right? And the problem is to find the unit vector u in the same direction as v, like this one. Okay, let's do that. So first of all, compute the length of the v, right? So what is the length of the v? So the inner product v and v, right? So in this case, the square 1 plus square negative 2, square 2, and square 0. So it should be 9, right? So in this case, the length of v is equal to 3, right? Now we know the length of the v, then we can multiply the v by 1 over length of v to obtain the unit vector u. So it will be v times 1 over v, 1 over length of v. So it was the 1 over 3, right? So 1 over 3 times 1, negative 2, 2, 0, right? So it means that the first entry is the 1 over 3, negative 2 over 3, 2 over 3, 0. Okay, so this is just the unit vector. Okay, so if you imagine the 4-dimensional space, because we cannot draw this one, right? Because we can draw the 3-dimensional space, even though it is very hard to draw, but we can draw that. We can draw this, right? But 4-dimensional case, we can draw this, right? But if you imagine there is one arbitrary vector v in the 4-dimensional space, then this unit vector means there is some kind of the set of point that whose length is just 1. So in two-dimensional case, it was something like the circle shape, right? What about 3D case? Will be something like the sphere, right? Something sphere. Then this is 1 2D space, this 3D space. What about this 4D space? So please think about this. Actually, I don't know, but anyway, the unit vector in 4D space will make some kind of the cluster, but in mathematical way, we can easily represent the unit vector u as follow. Okay, so this is the unit vector. Okay, so now we know how to measure the length of the arbitrary vector v or u. Then now we have a tool to measure the distance between vector u and vector v. So here's the definition. So for vector u and vector v in Rn space, the distance between vector u and vector v written dist u comma v is just the length of the vector u minus v. So it means that distance u comma v is equal to distance of the u minus v. So this is the definition of the distance. Let's see the what does it mean. Okay, so where's that? Yeah. So let's think about 2D space. If we have the vector u here and vector v here, we want to know the distance between this one and this one, right? Then the distance means the length of this one, right? So it means that the length of this one is length of this one, here, this one subtract by this one. So what does it mean? Okay, we have a matrix U here, matrix V here. So then if you remember the matrix operation, then U minus V is going to be this vector, right? So it means that length of this one, length of U minus V is equal to the distance between U and V, okay? So distance between U, vector U and vector V is defined the length of the U minus V, okay? So this is the definition of the distance, right? This is very intuitive, right? So actually you can also understand this concept in the 3D space or the 4D space, but you can easily understand in the 2D space, right? Because if some kind of the definition is defined in the 2D space, so then we can easily prove the same property or same definition also would be defined in the more high dimensional space, something like the Rn space, right? So anyway, this is the definition of the distance between U and V. Okay, so let's see the example. Let's say we have a vector 7, 1, and 3, 2. Then let's compute the distance between them. Okay, let's do that. First of all, if you draw the 2D space, vector U is something like this, right? And vector V is something like this. Why? 3, 2 and 7, 1, right? 7, 1, right? Then what was the U minus V? What is the U minus V? So in here, U minus V means this vector, right? So it means that this. Okay, let's see the values. So this is the 7, 1. This is the 3, 2. Then what is this vector? Because this is 7, this is 3, so this should be 7 minus 3, right? What about this? No. What about this one? This is the 2, -1, right? From 2 to -1 or 2 minus 1, right? So it means that this vector can be represent by this one and this one. Okay, so 7 minus 3 here, and it should be 1 minus 3, right? Because the from here to here, right? So it should be 1 minus 2, right? So 1 minus 2 is equal to negative 1. Okay, so this vector is the 4 comma negative 1. So the what is the length of the u minus v here? We can compute something like this, right? Square root 4 square 4 plus negative 1 square, so it will be the square 17, right? So as you can see here, this vector is defined, can be defined here, right? So it means that distance from u to v, this one, is same as the distance from the u negative v to 0 here. Okay, so the length of this one is equal to length of this one. Okay, so this is the definition of the arbitrary two vector u and v. Okay, so let's take a break.